Hello, my budding physicists. Let's start with a curious thought. If light from every point of an object sends out an infinite number of rays, how on earth do we ever manage to draw a ray diagram on paper? I mean, imagine trying to sketch all of them, the diagram would look like a plate of spaghetti. So here's the smart trick. We don't draw all rays, we pick only the special ones, the convenient rays. These rays behave in such a predictable manner that just two of them are enough to tell us where the image forms. It's like having VIP shortcut passes in physics, no crowd, straight to the answer. Alright, our first VIP ray, the one that goes straight through the center of curvature, point C. Picture this ray as a super stubborn person, it refuses to bend or change course. Why? Because the line from the object through C hits the mirror at 90 degrees, perfectly normal. And when angle of incidence is 0, reflection also comes out 0. So, the ray just retraces its steps like, nope, I'm going back the way I came. Easy rule, ray through C comes right back along its own path. This is like going to the grocery store, realizing you forgot your wallet, and walking back the exact same way home. Next comes the celebrity of ray diagrams, the parallel ray. Any ray that marches parallel to the principal axis is destined to meet the focus. In a concave mirror, the ray bends and converges at F, the real focus. In a convex mirror, it plays a trick. It looks like it's coming from F behind the mirror. It's like watching a magician's illusion. You see the ray going forward, but your brain extends it backward to find its origin. So the golden line, parallel rays always have a secret connection with the focus. Now let's reverse the trick. What if we send a ray through the focus? In a concave mirror, this ray exits parallel to the axis. In a convex mirror, a ray aimed towards the focus emerges parallel. It's like saying, if you go to the focus, you come out parallel. If you start parallel, you meet the focus. It's basically the mirror's BFF rule. Focus and parallel rays are best friends forever, swapping roles no matter what. Our final convenient ray, the one hitting the pole P of the mirror. Here the mirror behaves just like a flat plane mirror at that point. The ray reflects back, making the angle of reflection equal to the angle of incidence. Think of the pole like a well-disciplined referee in a football game. Whatever angle the ball comes in at, the referee makes sure it goes out at the same angle, but on the other side. So at the pole, the rule is simple, angle I equals angle R. Let's test these rules with an example. Suppose we have an object placed in front of a concave mirror. Step 1. Draw ray AP parallel to the axis. According to our rule, after reflection it passes through focus F. Step 2. Draw ray BD through the center of curvature C. This ray goes in and comes back along its own path. Now watch the magic, both reflected rays intersect at a point A1. That's where the image of point A forms. Join A1 to the principal axis and you get the image A1B1, which is real, inverted, and sitting proudly on the other side of the mirror. See? Just two rays, and we've nailed the image position. The mirror isn't messy anymore, it's crystal clear. So, to wrap it up, we've got 4 superstar rays to simplify our life through the center of curvature, parallel to the axis, through the focus, and incident at the pole. Remember, concave mirrors love converging rays to a real focus, while convex mirrors play the diverging illusion game with a virtual focus. And the best part, to locate an image, you only need 2 rays, not 1,000. Think of it like ordering food. You don't need to try every single dish on the menu to know if the restaurant is good. Just 2 specialties are enough. I hope you now see how convenient rays are the real shortcuts of ray diagrams. Simple, predictable, and exam-friendly. See you in the next session with another shining concept of physics.